Hey everybody, Dr. A here, and in this video we are exploring a torsional shear stress example. So let's look at the given information. We're being asked to determine the maximum torsional shear stress in the shaft. And the shaft is solid with a 1.5 inch diameter. So let's take a look at our 3D given figure here. This is supposed to be a 3D shaft where point A is fixed to some wall and point C is the free end. So this could be called like a cantilever shaft. So 3 feet away from point A, we have point B, and point B is supporting a 5 pound-foot torque moment. And then 2 feet past point B, we have point C supporting a 2 pound-foot torque moment. So this is our 3D view. All of this is given. So maybe pause the video and write this down. So under solution, the first thing I like to do is just write my governing equation. So the problem is asking for maximum torsional shear stress. So that's going to be tau max equals T max times a radius divided by a polar moment of inertia value, okay? So let's go ahead and calculate the quickest things first. So you're told that the shaft is solid with a 1.5 inch diameter. So that means that the radius is 0.75 inches, okay? And our polar moment of inertia for a solid circular shaft is given by pi times the radius to the 4th power over 2, or you could write that as pi times the diameter to the 4th power over 32. Either one will get you the same answer. So let's just use the radius version. Pi times 0.75 inches raised to the 4th power over 2. I'm going to use my TI-36X Pro calculator to determine that. So I get a polar moment of inertia value of 0.497 inches to the 4th, and track those units, okay? Remember, it's a moment of inertia. J is polar moment of inertia. It has units of length to the 4th power, okay? So that takes care of two of these components of the equation immediately, R and J. Now, what about tau max? I'm sorry, T max. What about T max? So let's write this down. To determine T max, we can either draw a torque moment diagram or use method of sections. So at this step, it's actually a static step that we're looking into to get T max, okay? Whether you draw a torque moment diagram or use method of sections, either of those techniques are from statics knowledge, okay? I'm going to use method of sections. So let's go ahead and write that down. Let's review that. So let's say let's use method of sections. So what is method of sections? Well, if you remember from statics, method of sections is a technique that we use where we place a kind of a non-realistic cut section through our member at desired points or within a desired domain to determine internal loads, okay? So for example, when we use method of sections, we're going to have to make 2 cut sections in this shaft. We're going to need to make a cut section within the domain between B and C, because that 2-foot domain is where we're going to have some constant values, and then we're going to have to make a separate cut section between point A and B, again, because on the domain from A to B, we have constant values, okay? So again, review your method of sections from statics if you're a little rusty on that, because I'll talk through a little bit of review points for it, but I'm not gonna reteach method of sections from scratch in this video, just gonna hit the highlights of it, okay? So let's go ahead and do that. So let's use method of sections, and we're gonna make our first cut in BC, okay? So if you remember, we make a cut inside of BC, and then when we do method of sections, we need to sketch everything that's on one side of that section. So in my case, I'm going to sketch everything to the right of the cut. So I've made a cut right through here, and I'm sketching everything to the right of that cut, including that applied torque moment of 2 pound-feet. And then what happens at the cut? Well, at the cut, you're going to expose your unknown internal load. I'm going to call this TBC, okay? And remember, this is an unknown internal load, which means that you don't even know its direction. So this is an assumed direction. The next thing I'm going to do, because this is still kind of a three-dimensional shaft, I'm going to draw what I call a viewpoint, okay? I put a little eyeball here with some eyelashes, and I draw the direction that I'm looking when I'm getting ready to write my equilibrium equation. So I'm putting this little eyeball here, this viewpoint, and I'm going to look into the cut that I just made. So what do I see when I look into that cut? Well, I'm going to see this circular shaft section, okay? And I'm going to see that unknown TBC. And then behind it, I'm going to see the known 2 pound-feet. Okay, so again, using this viewpoint, this little eyeball, I'm looking into my cut section. What do I see? I see a counterclockwise TBC, which again, this is an assumed direction because right now TBC is unknown. And then behind it, it's not really on top of it, but it's behind that, I'm going to see my known 2 pound-feet. So I drew it kind of like as a hidden line, this dashed line, to indicate that it's really behind TBC. And then I'm going to write my torque equilibrium equation. Sum of the torques equals 0. Counterclockwise is positive, referring to this viewpoint, reviewing to this viewpoint here. And I'm going to say TBC plus 2 pound-feet equals 0. Of course, TBC becomes negative 2 pound-feet. And what does that negative indicate? Well, we can write that as 2 pound-feet with TBC rotating actually clockwise. So TBC is actually, that internal torque TBC is rotating opposite of what we assumed because it was negative, okay? So again, all this is a method of sections technique. Next, I'm going to make my other cut in AB, in the domain AB, and I'm going to follow a similar process. Now here, I'm making this cut in AB, and again, by method of sections, we're going to look at everything on one side of the cut. So I'm going to choose to look at everything to the right of the cut. Again, remember, for method of sections, you could look at everything on either side of the cut. It doesn't matter what side of the cut you analyze, since the whole thing is in equilibrium. The whole, figure is in equilibrium. But just to avoid this external reaction here, I'm going to look at the cantilever side to the right of my cut. So, and that's going to include everything that's acting on it. So I've still got my 2 pound-feet here. And then at this point, I've got, what was that value? 5 pound-feet at point B. And then we have a 2-foot dimension line in between those two. And then I have this unknown TAB. Again, I'm assuming this direction because it is currently unknown. I'm going to put a similar viewpoint here. I like to draw a little eyeball here and a dashed line to show which way I'm looking. And so you ask yourself, what do you see? What does this eyeball see when it looks inside that cut? Well, it sees the solid circle here, and then it sees the unknown TAB going counterclockwise. Behind that, it sees the 5 pound-feet, and then behind that, it sees the 2 pound-feet. So practice this visualization skill and make sure you can see these directions like I'm sketching them here. So we're going to write sum of the torques equals 0, counterclockwise is positive, and we're going to have a TAB, and then we're going to have minus 5 pound-feet, and then we're going to have plus 2 pound-feet equals 0. and we'll get TAB equals, move that to the other side, so we have 5 minus 2 is 3 pound-feet, and it is, in fact, oriented counterclockwise. And so since the absolute value of TAB is larger than the absolute value of TBC, then we're going to say T max is equal to TAB, which is the 3 pound-feet. And now we're ready to go. We're going to say tau max equals T max R over J. And so that's going to be 3 pound-feet. Now we got to be careful here. This is 3 pound-feet. We got to convert this to pound inches because our radius and our polar moment of inertia are also in inches. So we have to have consistent units. So we're going to say 12 inches per foot to create this conversion where we can, cancel some feet here, and we'll have pound inches. And then we're going to say times the radius, which was 0.75 inches, and then all divided by the polar moment of inertia. Let's remind ourselves what that is, 0.497 inches to the fourth. And I'm going to use my trusted TI-36X Pro calculator again. So we have 3 times 12 times 0.75 divided by 0.497. And I get 54.3 pounds per square inch. And if you remember, a pounds per square inch is also known as PSI. So watch those units. See how you get the PSI, okay? Let's use different colors here. We have 2 of these inches that combine to make inches squared, but then those will cancel with 2 of the inches in that denominator, leaving inches squared in the denominator instead of inches to the fourth. So finally, you're left with pounds per inches squared, okay? So maybe pause the video, make sure you can track those units. But again, it makes sense, right? This is a stress. Is torsional shear stress? What are the units of stress? Stress has units of force over area. So in this case, pounds over square inches. So watch those units, okay? So that's going to conclude this example. If you liked it, please hit like and subscribe. Thank you.